Hello, we are group 27 and we are EnduraGraft. A bone graft is defined as a surgical procedure in which transplanted bone is used to repair diseased or damaged bones and assist in healing, strengthening, and bone function. The anticipated market potential of the industry was at $3.3 billion in 2013 and anticipated to see a compound annual growth rate of 13.8%. The market for bone graft products is expected to grow significantly. This can be attributed to market drivers such as an aging baby boomer generation, increase in success rate of surgical fusion, increase in number of spinal surgeons, and the growing acceptance of bone graft products due to positive clinical data. Autograft is the most practiced form of bone grafting, in which a bone or tissue is transferred between two places on one person's body. An allograft is defined as the transplant of an organ or tissue from one person to another. Additionally, there are various synthetic materials used for bone grafting, which are becoming more popular as technological capabilities advance. Alloplastic grafts are typically comprised of hydroxyapatite, a mineral which is found in natural bone, therefore giving it the ability to mimic bone, giving it an excellent acceptance in the body. This acceptance allows for the alloplastic graft to have osteoconductive abilities, and the synthetic bone scaffold is manufactured using bioactive glass to have similar hardness to that of natural bone. Synthetic bone graft variants can also be created using ceramics such as calcium phosphates and bioglass. These materials are desirable as bone grafting substitutes for their bioactivity and ability for enhancement via doping with growth factors. During autografts, it has been documented that the second surgery required for spinal fusion can cause morbidity in more than 25% of patients. Furthermore, there's a risk of post-operative infection and fracture of allograft when using donor bone and tissue. Additionally, patients experience long wait lists to receive donor bone and tissue. There are also inherent limitations of alloplastic grafts, such as long-term implant instability, rejection by host body and infection, injury to nervous system, loss of osseointegration. For ceramic grafts, limitations include poor response to lateral forces, poor response to frictional forces, potential voids created by manufacturing defects leading to lower compressive strength, and instability over time due to high temperatures that hydroxyapatite is processed at. As seen, current methods are insufficient at providing mass bone grafting options with minimal drawbacks. Clearly, there is need for a product that can provide an affordable and reliable option to people all across the world and help them skip the wait list to restore their body back to better health. Introducing EnduraGraft, a graphene-based solution that can be mass manufactured through spark plasma sintering. But before we get into our solution, I first want to show you how we got to this point. To ensure the resulting product has superb biocompatibility, advanced manufacturing techniques must be explored to replicate the complex porosity, shape, and density of human bone and tissue. In order to improve on the status quo of bone grafting and implants, we are aiming to provide consumers with a product which is mechanically superior, more affordable, and forms a stronger interface with host tissue. To achieve this, we look towards a novel method to engineer highly porous and mechanically superior scaffolds.
The design of a bone grafting product has many considerations. For the biological considerations, it is mostly the compatibility needs of the bone tissue. Essentially, the graft must be able to effectively promote efficient bone growth that will produce a strong bond with the implant. Mechanically, the graft should be similar to native bone tissue in order to prevent issues that may result from loading and have minimal impact on the patient, such as having similar weight. Porosity also contributes to bone adhesion, promoting stability.
The three main factors at play in designing our product are spark plasma sintering, graphene, and graphene oxide. Spark plasma sintering is a novel thermomechanical powder processing technique based on pulsed electric current, material heating, and uniaxial pressure. This allows for sintering to be carried out at accelerated rates, which minimizes energy and time demands, and results in a material structure which retains its nano-sized grain structure, allowing for high strength. Graphene is a 2D carbon layer with extremely high strength, stiffness, and electrical conductivity. This has been researched for its potential to revolutionize several different industries and has proven biocompatibility and ability to activate, promote bone tissue formation. Finally, graphene oxide is a more economically accessible version of oxide form of graphene. This version is hydrophilic and soluble in water environments and not suitable for most structural applications. In the process, the spark plasma sintering involved with the process begins with the use of graphene oxide and preparing the material in a green body state, which is then maintained under uniaxial pressure. The spark plasma sintering allows for the graphene flakes to undergo rapid heating and instantaneous localized welding due to the pulsed current. As a result of this process, the reaction kinetics of the system results in a reduction of graphene oxide into its pure graphene form, allowing for a pure graphene nanostructure to be obtained. This structure is capable of maintaining a high porosity and excellent mechanical properties, making it suitable for use as a scaffold matrix. The technical procedure of creating the product has 5 key steps, the first of which is graphene exfoliation. In order to prepare the as-purchased graphene oxide flakes, they must first be exfoliated by separating the flakes through a ball milling technique and then filtered using a 20 micrometer mesh sieve. Once ready, the powder will be poured into a cylindrical graphite die of various sizes depending on the customer requirements. This will then be compacted by hand. The die ready, the sample will be placed inside the spark plasma sintering machine, and the machine will be set to operate at a heating rate of 75 Celsius per minute, a nominal applied stress of 50 megapascal, and a final temperature of 300 Celsius. Once cool, remove the samples from the die and prepare for packaging. One possible option for a final step is growth factor doping. In order to increase its effectiveness in grafting, testing shows that low oxygen content graphene doped with mesenchymal stem cells resulted in significantly increased bone formation and mineralization.
There are many strengths for a graphene scaffold over existing grafting options. As a synthetic scaffolding material, this can be considered to have a significantly longer shelf life over live donor samples. It is very biocompatible and greatly promotes bone tissue growth and should be expected to integrate well with the existing bone structures. There is high customizability possible with capabilities to be used at any size level injury that may need bone structural support and/or complete replacement. The weaknesses of this as a product include the fact that this market is already fairly saturated with a wide variety of competitors, and it will be difficult to start competitively as this product would have a relatively high cost associated with it. The biomedical industry is also heavily regulated, with the approval-seeking process potentially taking many years and a lot of resources. One of the potential market opportunities for development is the use of graphene technology for the coating of medical implants, such as dental implants, which would allow for superior bone integration and stability. Another option is to focus on larger scale bone replacements that are currently not possible with other options. Some of the threats to this product include possible low-cost ceramic composites, which could be used for smaller scale grafting or implant coatings.
In order to optimize the product, a design of experiment will be carried out. This will be carried out to accomplish a 3-level design with 3 control factors. It will be required and optimized through a full factorial run. This will require 27 test runs and will provide insights into any 2- or 3-way interactions between the 3 control factors. The temperature will be altered in order to find the critical point for graphene oxide reduction and high temperature impact on scaffold structure. Sintering time will be altered in order to identify the impact of sintering time on graphene oxide reduction and any porosity changes in graphene welding. Finally, pressure will be altered in order to identify the impact of ambient pressure on the porosity of the structure.
In conclusion, existing bone grafting options have benefits but also their own drawbacks, such as rejection or cohesion failures. Graphene is biocompatible and has excellent mechanical properties, allowing its use as a potential scaffold or implant. Spark plasma sintering can be used to create bulk 3D structures out of graphene oxide powders. And as this is a novel technique, more research will be required. However, this initial overview appears promising.